And just like that, we are finally here. Hello, worldly crazy people out there. My name is Michael. I like wizards and dragons and making games. Welcome to the optimization video of 3D collisions in GameMaker. I have added pretty much all the functionality to the system over the last 38 videos that I really care to, and today, I'm going to talk about how to make it faster. So this video is going to get a little bit micro-optimization-y. I'm going to say the bulk of what I'm going to talk about is going to be more, well, macro optimization, mathematical tricks, avoiding doing work that we don't have to, that sort of thing. I'm not going to change any of the algorithms that I'm using in this 3D collision system to make the system faster as a whole. Although, make no mistake, there are other algorithms that you can use for this. The separated axis theorem is nice in that it's easy to explain, at least relatively, but the number of axes of separation that you have to check does tend to be a lot. And there are definitely other somewhat faster algorithms that you can use in place of it. But I'm not going to get into that now. So I've recently made a few videos on various optimization-related subjects in GameMaker. The profiler in the debugger is something that I'm going to be leaning on a lot in this video, so if you've never used that before, it is something that is definitely worth getting familiar with. I will have a link to that video in the description and in a pop-out card. I also, a little while ago, did make a video on the mother of all micro-optimizations, which is actually looking at the GameMaker bytecode to see which operations use fewer GameMaker virtual machine instructions. Again, I'm not going to be getting too micro-optimization happy in this video, but knowing generally how that works may provide a little bit of additional context to what I'm about to say for the next hour or so. And one way or the other, I know that is the sort of thing that some of you nerds do find interesting just inherently, so I will have a link to that video as well. What I'm not going to do is go through each and every line of code in this project with a fine-tooth comb and see how much more performance I can squeeze out of it. If I were to do that, then this video would end up being about 15 hours long, and I would be in a retirement home before I finish editing it. But I am going to talk about a handful of broad classes of optimizations that you can do. I'm going to show a few different situations, at least one or two different situations where they can be used and what kind of performance gains you can expect, and you should be able to extrapolate from there. There are a few things I'm not going to discuss here. First and foremost, there's the usual CPU micro-optimizations. I've ranted about this in the past, and I'm going to do it again. I'm going to keep on dividing by 2 instead of multiplying by 0.5 wherever it makes sense. I'm going to keep on using the square root instead of distance squared. I wrote a benchmark tool for GameMaker. If you can prove to me that dividing by 2 is slower than multiplying by 0.5 in any capacity that extends beyond statistical noise, then we can talk. But if not, then I'm really not interested in hearing it. There's also a few tricks involving setting up your collision world that you can use that can definitely save time, but I don't really have set up to demonstrate here. If you must use a triangle mesh for collisions for any reason, you can almost always get away with using a much simpler triangle mesh for collisions than you would use for the visible model. For example, if you had this model of a house, then instead of using the fully fledged model for collision purposes, you could just as easily get away with using a much more simplified model of the house. And that would be a benefit not only because there are fewer triangles to process for collisions, but also because if your house has very dense geometry, then there's the possibility that your character will just get stuck on a piece of geometry that's sticking out of it, and that'll be another rather unpleasant experience for the player. And a lot of the times you could also just as easily use, instead of a triangle mesh for the house, just a series of primitive shapes. So maybe a couple blocks and maybe a capsule for the chimney or something like that. And there are also a few different kinds of GML optimizations that I was initially going to include in this video, but I probably won't for the sake of time. If you're a fan of repeat loops instead of for loops, then you can go ahead and use whatever repeat loops you want instead of for loops. The system is kind of designed to avoid having large arrays anyway, so I don't think it would be that much of an issue. There's a couple places in the code where you might find the same value calculated multiple times, either because just by accident or because I thought it was more readable. And in situations like the calculating the vertices for an ob, there's a couple of redundant calculations in there. You can rearrange that as you see fit. I'm going to be talking about the vertices of an ob for a different reason later in the video anyway. There are a few miscellaneous things of that nature in this project that you could squeeze a little bit more performance out of, but given how long last week's video was, and given how long this video is going to be, I think I'd rather not spend an extra 5 or 10 minutes of footage just searching for those and showing how they take off like 10 extra microseconds in the profiler. So that's what we're not going to do today. Now let's get into it. So this is the 3D collisions testbed that I've been using. As a general reminder, it looks something like this. You can summon different shapes, and you can test for collisions with different shapes. To make the performance costs of a bunch of these things a little bit more obvious, I am going to throw the code that's doing the collision checking in a little repeat loop, and we're going to do this 100 times per step instead of once per step. And this should obviously take a little bit more time, so that when we look at the FPS_real, or more correctly, when we look at the frame timings in the debugger's profiler, we're going to be able to see somewhat more of a difference. So let's start with something easy. So by and large, the cheapest collision check that it's possible to do in GameMaker, aside from checking if like 2 points are equal to each other, which is something that I don't think I'm even going to call a collision check, the cheapest collision check that you can do in GameMaker is going to be checking to see if two spheres are in contact with each other. All that is getting the distance between the two centers of the spheres and checking if the distance between the centers of the two spheres is less than the sum of the radii. So with that knowledge in hand, if we were to treat some of the other shapes in the system as spheres, and if we were to check the distance between the sphere and the other object, and check if that distance is less than the sum of the radii of the sphere and whatever you might consider to be the radius of the other object, then you could use that to potentially eliminate quite a lot of work. And if you can cheaply and effectively rule out the possibility of the two shapes being anywhere near each other before doing the more precise, more accurate, and more expensive collision checks, then you can potentially save quite a lot of time when you're doing your collision checks. So let me run the game, and I'm going to test a sphere versus an ab. And I'm going to run the game, and I'm going to look at how that performs in the debugger's profiler. So that's going to be a sphere, that's going to be an ab. I'm going to move them apart from each other. We're going to see how that performs. 700 or so FPS_real. If I were to look at the profiler, we can get a beat on the performance of the individual things that we're doing in here. So 100 different collision checks. All right, let's get that step percentage out of there. Let's focus more on these two values. We can see that we're doing a few sphere ab checks. We're doing a few, I believe this is the nearest point on an ab. If you do that 100 times, that's going to take up about 800 microseconds per frame, which isn't dreadful, but we can optimize that a little bit if we can rule out the fact that these two shapes are going to be anywhere close to each other. So I actually touched on this a little bit when I dealt with frustrum culling, because like trying to precisely check a frustrum against an ab or an ob it would have been so expensive that I didn't even want to think about it. If we were to envision a circle, if we were to envision a sphere that perfectly circumscribes an ab, which by that I mean a sphere which the radius is going to be equal to the greatest distance between the edge of an ab or an ob and the center. If we were to do that, the radius of the sphere would just be the magnitude of the half extensor, the magnitude of the size vector in one of the box shapes. And let's start off by saying var distance is going to be equal to, let's say ab dot position dot distance 2 self dot position. We can say ab radius is going to be equal to the magnitude of that half size, and we can say if distance is less than, or rather distance is greater than ab radius plus self radius, then we know that it is not possible for the sphere to be in contact with the ab because it is farther away from the ab than the greatest distance, like the greatest extent of the ab, basically the distance from the center to one of the corners, and we can return false. And if I were to run the game in debug mode again, let's summon a sphere, let's summon an ab, let's move them far apart from each other. Let's have a look at the profiler. And we can see that this is now a lot faster than it was before. We can early out, we can avoid having to do all of this work involving the nearest point and calculating the nearest point or whatever, which is it's not horrendously expensive, but you can see it's quite a few additional mathematical operations. And as a result, we've gone from about 1.5 seconds it took, I think, to run all 100 of these sphere ab checks down to about a third of a millisecond. 1.5 milliseconds, rather. 1.5 seconds would have been dreadful. And what kind of FPS underscore real are we getting? About 1,000 or so. 1,500. So we can say that in cases where these two shapes are nowhere near each other, we have a triple performance. Now, this will actually be a little bit more expensive if the two shapes are actually in contact with each other, because what we're now doing is we're now doing everything that we were doing before with the nearest point and the distance and all that, but we're also doing this on top of that. And if I were to run the profiler now, that would be reflected. So we're going to be doing everything that we were doing before, but we're going to be doing some additional vector math. And while it's not the most expensive vector math, it's also not nothing. We're getting 400 to 500 FPS underscore real now. I'm gonna say that's about another 1/10 of a millisecond to do that. So that's just something to keep in mind. On average, assuming that when you're doing 3D collision checks against the world, assuming that most of the objects that are in the quad true node or the spatial hash chunk or whatever are not like all stacked on top of each other and all stacked on top of the thing that you're trying to check collisions against, on average, I would expect this to be a net benefit, but do keep in mind that in the worst case, it is doing slightly more work. And we can do the exact same thing for spheres and obs, and as I did allude to, spheres and a bunch of other shapes. So if I were to take an ob and if I were to take a sphere, and if I were to look at the profiler, I don't know why I closed the game. How are we doing? This is taking a little bit longer. This is taking about 2 milliseconds to do 100 of these, which not dreadful, but it's something that we can improve. So if I were to take this, and if I were to go into, I believe, the ob check sphere, rather, we can do pretty much the same thing. So instead of, I'm going to have to reverse the operands here because they're in the opposite order. So the sphere is the incoming parameter, and the ob is our self. The ob radius, as I'm going to call it, is going to be the magnitude of the size over here. Okay. Nothing too different from what we had before. And if I were to run this again, and if I were to look at the profiler to see how we're doing, let's move those two shapes so that they're not in contact with each other. We can see that we've gone down from, what was it, about 2 milliseconds in total to do all that, down to 0.2. A little more than 0.2. So let's take a conservative guess and say that we've improved this by about, say, 7 or 8 times, just by doing that one early out. The nearest point on an ob is slightly more expensive than nearest point on an ab, because we also now have to account for rotation, which is a little bit of a whole thing, but we can still get a bonus there. So the logical extension of this, the logical next thing to do with this would be, what if we were to use this trick with two shapes that are not actually spheres, neither of them are spheres, but we can still pretend to have a radius. So let's say that if we were doing ob versus ob, that is, as you are probably aware, a fairly, numpad 7 is going to be another ob, a fairly expensive operation. You can see we are getting about 4 FPS here, and it's actually going to take me a little while to move these two shapes out of contact with each other, because this is just, when we're doing this 100 times, this is just that expensive. And when they're separated, it's performing a little bit better. We're getting about 50 FPS underscore real doing this 100 times, because don't have to check every single axis against every single other axis now before we can find an axis of separation. But all the same, if I were to profile this, and if I were to look at how this is doing, this is all taking 20 microseconds to do it 100 times. That's a lot. And if I were to if I were to pretend that both of these shapes are spheres, then we can do functionally the same thing that we were doing before, and we can potentially save quite a lot of time, which is lovely. So let's summon an ob, let's summon another ob. You'll have to give me a minute to move these apart from each other. And in the amount of time that it took me to hold my finger down on the arrow key and separate those two shapes, I probably could have just like edited the code so that they don't spawn on top of each other, but here we are. So you can see it's now performing a lot better. And if we want precise metrics on exactly how it's doing, we can look at the profiler. And instead of taking about 20 milliseconds to do this, this number of times, we are down to 0.2 something milliseconds to do this number of times. So you can make a legitimate claim that by doing this, we have improved the performance of ob versus ob, at least in some circumstances, by a factor of 100. And I think that's pretty nice. Got that for basically free. Or not free, but just by doing a tiny amount of extra work on top of the separated axis theorem. So I'm going to count that as one category of optimizations that you can do, and you can do this with a lot of different shapes. Any shape that isn't infinite in some direction, any shape that you could claim has a center somewhere, you can do this with, so that's going to be not only abs and obs, but also things like triangles, capsules, you can do this with. You'll have to do a little bit of extra work to figure out the center of a triangle because it's defined by 3 points and not like a center and a size, but you can do it, and you probably remember how expensive, for example, triangle versus triangle code is. Where is it? It's in here somewhere. Oh, it was collapsed. You probably remember how expensive triangle versus triangle code is. And if you can just do a little bit of a distance check to early out, then you could potentially make triangle run a lot faster. Although, to be honest, if you can avoid doing triangle in the first place, that would generally be ideal. So I'm going to let's commit some of these changes. I'm going to go back to the oriented bounding box because obs are probably, aside from triangle meshes, obs are probably the most expensive shape to compute collisions with in general. And a large part of that comes down to the fact that anything that involves obs and the separated axis theorem, and also a few other things that involve obs, will involve a method called to this getVertices method. And the getVertices method is going to populate an array of 8 points in space, which represent the corners of the ob. And this is also true in ab, but the math when it comes to abs is a lot friendlier. And you can just see how many vector operations this involves. So for each of these 8 points, there is an add, there's a multiplication, 2 adds, 2 multiplications, 3 adds, 3 multiplications. So that's going to be 6 bits of vector arithmetic times 8 is going to be 48 vector arithmetic operations every time you do this.
Hey.
And that's a lot of math. That's a lot of allocating structs representing these vectors, and that is also something that goes rather unappreciated a lot of the time. A lot of time that the garbage collector is going to have to go through to clean up those structs when you're finished with them. So what if there is a way that, if we know that the values of the corners of an ob aren't going to change, what if we didn't have to calculate this over and over and over and over and over again and do all this extra math and allocate all this extra memory if we knew that the positions of the corners of the ob was just the same as it was the last time you did this operation? And now we're going to start to talk about caching. And this is going to go for a number of different properties and a number of different shapes. So you can do this with vertices, you can do this with edges, minimum and maximum extents of a lot of the different shapes. You might recall that minimum and maximum also rely on get vertices when it comes to abs and obs, same for get edges. So if we were to take this, and what if in the constructor we were to simply save all this as a variable, and instead of having to recalculate it every single time, when you wanted the vertices of an ob, you could just say access that array that already exists. And again, this is going to be the beginning of where I talk a lot about caching. First, I actually, let me undo that. And let me actually, oh, it's already running. Let me move these closer together again. And if I run the profiler, let's just see how horrifically bad this is going to perform. And exactly how much of that computation time is going to be taken up by calculating the vertices of the two obs every single time. So if I let that run a minute, and I'm just going to close this so it's not chugging away in the background and eating my CPU cycles. We can expand this. We can see that call overlap access is what calls the get interval method, which in turn is what calls the get vertices method of the ob. And we're doing this 3,000 times in total. That's taking up 250 milliseconds per frame, which is a quarter of an entire second, hence why we're getting a little bit somewhere between 3 and 4 frames per second. You can see that we are calling, I don't know which vector operation this is. I think this is add, or I think this is multiplication, 77,000 times. That is accounting for about 100 microseconds per frame. Addition and subtraction are being called half that. Those are accounting for about 50 microseconds per frame each. That's a lot. We're also allocating a lot of new structs every time we do that. And if I actually switch this to the bottom-up point of view and sort by the call count, we are allocating 160 new structs. 160,000, I'm sorry, new structs to do 100 ob versus ob checks. And that alone is taking up 120, about an eighth of a second, which is just absolutely insane. The snitter was actually making fun of me for, doing so much of that a few days ago, and then I told him that I was gonna work on this. And then he was like, oh, thank God. Anyway, so if we switch over to caching this over from doing all that work every single time, performance will be improved, but you will have to remember to do one additional thing, and that is that what happens if the position or the size or the orientation of this ob changes at any point, which is in fact what is happening in this system when I'm moving the shapes around, and which is what will be happening most likely when you actually use this in an actual game and you have objects that are moving around. And to deal with this, it is going to be rather helpful to go full object oriented and say, let's define some set position methods, and this is not only going to set the position of an ob, but it's also going to let's say recalculate all these values to make sure that the vertices positions are all up to date. I'm also going to have to go back to my test file, and when I test an ob, when I reposition an ob. So now, when we update the position of the collision shape, we are going to have to call the set position method to ensure that any values that need to be updated are updated. This is a common thing to do and to see in object-oriented programming. GameMaker, as you all know, does not have private, protected, public variable access when it comes to structs and properties and things like that, but using mutator methods for things like this would be a good idea all the same, just in case you need to ensure that something like this is updated whenever the need arises. And if I were to rerun this now, let's see, ob and ob, you could see that right off the bat, performance is a lot better than it was before. Again, that looks like about a 10 times improvement over what we were doing before. Let me look at the profiler, and if I were to sort by the amount of time, we can see that we're down to about 36 milliseconds to do this 100 times, down from like an entire quarter of a second, which is definitely an improvement. There are still things that could be improved in here, but the important part is that the Which one was it? I think this one, I think, will be the get vertices method. This is no longer taking up an entire quarter of a second to do that as many times as we were. There are still other things in here that are taking up a lot of time, so this is going to be the get interval method. I think this selected line over here is taking up 30 milliseconds. The one vector dot product method is being run to 24,000 times, all told, and it's taking up about 10 milliseconds of that. But we have eliminated by far what is the largest source of the slowdown in the setup here. If I were to move the shape out, not quite far enough out that we can just do the sphere check, but far enough out that there is indeed an axis of separation somewhere, we can see that it is running a little bit better still. And that is the benefit of caching these values. I don't think when it comes to ob versus ob, get min, get max, get edges are called anywhere. I think these are used mostly for other shapes. But you can also likewise cache the edges up here like this, and you can also cache the min and the max. And let me just cut away to myself doing that. This shouldn't take long. So now with that, get edges, get min, get max are all going to be much cheaper to call if the values haven't changed since the last time. This obviously is a little bit ugly. This is a little bit of duplicated code. Generally, duplicated code is not a great thing to have. So what I'm going to further do to make this just a little bit neater is add an additional method, and I'm going to call that recalculate properties. And I'm just going to call that wherever the need arises. So that'll be in the constructor itself. That'll be in the set position method if you wanted to do more of this for set size and set orientation. You could also do that. Also, I don't know why I wrote mat4 here. That is a matrix 3, not a matrix 4. Anyway. When we update our size and also our orientation, we are also going to recalculate any relevant properties. And I don't think that is something that, I don't think that'll have an effect on ob versus ob. Some of the other shapes, that'll be relevant too. I don't remember which ones off the top of my head. Transform model apparently is where min and max show up mostly. And ob versus capsule is where I'm using the edges. Alright, not sure if I'm going to show that off now, because I'm sure you will get the point after ob versus ob. As with the sphere checks, as with the radius checks, you can do this with most, if not all, of the other shapes. There are various properties, any min-max that has to be calculated, any vertices, any edges that have to be calculated. You could even do this in some of the more out there collision checks, like you could cache. A lot of the line cast checks depend on turning the line into array and doing a ray cast check, and you could cache the call ray that represents a line, like the distance, the direction from its start to its finish, so that you don't have to do that constantly over and over every single time. You can do it with things like the triangle's normal. Where is the get normal of a triangle? Get normal of a triangle, get plane of a triangle. Anything like that. Triangles obviously also have their own min and max bounds. You could also do this with like the imaginary radius of abs or obs. So if you wanted to take this farther, you could, when it comes to like ab versus sphere, and this is definitely going to be one of the less significant optimizations that you can do, but when it comes to ob versus sphere, instead of calling self.size.magnitude over and over, you could make magnitude one of the properties that is calculated. I'm going to call it imaginary radius. And you could simply check for these shapes, where was it? Imaginary radius instead of recalculating that. So let me actually go back and have a look at the profiler to see how ob versus sphere was, because I don't remember off the top of my head. So when we do this in obsphere, in the case where they're not in contact with each other, there's actually two vector operations that are being used here, and they both look similar. They're both some kind of distance formula. And I don't know which is which, but in any case, that is going to be 40 microseconds or 30 microseconds or something that we don't have to do. So if I were to check the imaginary radius instead of doing the vector magnitude every time, this is definitely going to be micro-optimization-y, but we are going to be going from, let's say, a quarter of a millisecond to do this 100 times down to some smaller number to do this 100 times. That's not an ob. That is an ob. Let's move those out. Let's look at the profiler. Okay, so you can see it's not world-changing, but it's also definitely not nothing. The first things that I talked about, the sphere checks and the caching, those are the big items that are going to be accounting for, like, pound for pound, most of the performance optimizations that you'll get out of the system. And now we're starting to get into the less significant things that are still add up over time. So another minor change that you can make that will probably start to add up over time is a lot of these abstractions for vector methods that we're calling. So I've got this big ol' vector library, right? So I've got vector add, subtract, basic arithmetic, as well as like magnitude, dot products, cross products, normalize, and that sort of thing, absolute value. And the math inside those vector methods itself isn't going to change, but there is a small, and I do mean small, but over thousands of function calls, it will start to add up. There's a small amount of overhead involved in actually calling a method itself. And if you were to, instead of saying distance equals self.position.distance2, if you were to say distance is going to equal just the actual point distance 3D, if you were to do this manually, you would also say some amount of time. So the vector distance method was taking about 50 microseconds in this operation here. And like you can see that the point distance function itself was taking much less than that. And about 40 of those milliseconds is just the difference in time that it takes to do the actual method call. And if I were to cut out the middleman and do this myself and write it out the long way, we should see that we're going to get another small, that's a sphere, and that's an ob. We should see that we're going to get another small, but not completely trivial performance gain from doing this. So what were we? Originally, I think it was about a quarter of a millisecond to do 100 of these, and then we cut that down to like 0.2, and now we're down to like 0.18 that we just got by eliminating that middleman. That's definitely a small amount, but there are plenty of places in this code where you can do this. So there are a ton of places where you can do this. If you were to look in, if we were to go back to like obs, what was it, get interval. We're doing a bunch of dot products, so we're doing a bunch of vector dot products. And if you were to do the dot product yourself here, so if you were to do ob versus ob, where the two obs were in contact with each other, you would go from this result on the profiler, so this many dot product calls, and they would take up this amount of time. And if you wanted to instead do the dot products manually like this, then you could shave off a little bit more time. This is what the profiler looks like now. Additionally, you could really juice this. You could really squeeze some more out of this, and you could accessing values from a struct itself takes time, a little bit more time than accessing a local variable. So this is definitely getting into micro-optimization territory, but if you were to save, for example, axis x, y, z as local variables, then you could save a little tiny amount of time on variable axis. Likewise, let's reformat this a little bit. Let's refactor this a little bit. So we can say the initial minimum is going to be infinity. The initial maximum is going to be negative infinity. We're going to loop over from 0 to 8 instead of 1 to 8. And we could also cache the vertex instead of doing an array axis. And this will also save an infinitesimal amount of time versus what we had before. I am not convinced that this is actually going to be enough of a change to actually show up as a result on the profiler. If I were to run this example, and if I were to summon two obs, and if I were to look on the profiler, it looks like we are... Alright, so it's not nothing, but it's definitely a small amount. Let's see, we're doing the dot product manually this many times, and it's come down a little bit from what we had before. Not nothing, but it's also not gonna magically fix your performance errors. And again, you can do this in all kinds of places throughout your code. Most of the 50, 60 something collision checks that I've implemented in this series are going to have some kind of like vector arithmetic that you could cut out the middleman for. You could even, if you really wanted to, forego doing things like vector add, multiply, basic arithmetic on a vector, and you could, instead of really using that many vectors, you could just have a free floating jumble of x, y, and z variables. I do not recommend that. Even doing things like this, like I was using the abstraction for vector magnitude and dot product and distance for a reason, right? That reason being that the code is elegant, the code is pretty short, and I don't have to worry about accidental typos slipping in where they don't belong. Whereas if you were to write this out the long way, every single time a dot product or a cross product or something else like that appeared in this system, there's a good chance that somewhere along the line you're accidentally going to do something like this, or you're going to accidentally do something like this, and you're going to suddenly have the wrong answer, and your collisions aren't going to work properly, and it's going to be really hard to diagnose why that happened. I actually spent a lot of time dealing with that sort of thing when I was like preparing this video and trying to get a measure on like how effective different optimization strategies were. So you can totally write out math the long way like this. If I were to extrapolate from here, I'm going to say you would see maybe like a 5-10% improvement in the system as a whole. But at the same time, you definitely have to be really, really careful to make sure that you don't let easy typos like that slip in. So there's one more thing I think I'm going to talk about, and that is, and I don't remember. Okay, here's an example. So let's do triangle versus pretty much anything that involves nearest point. So let's say triangle sphere. Allocating temporary shapes and temporary structs like vectors and that sort of thing in general. Allocating a new plane or a new line multiple times whenever you do a nearest point check for a triangle, or whenever you do anything else like that. That's another thing that adds up. It does take time for GameMaker to request the memory that the struct is going to need. It does take time when you're finished for the garbage collector to check that additional memory, see that it's not in use, and free it. And this is honestly like an easy case here, because it's not hard to do a like replace this with the manual triangle point code, right? Because that's not complicated. But if you did want to allocate a new point and use the checkpoint method on it, instead of making a new one every single time you did this, you can rely on static variables inside functions and inside methods to only have to allocate this once. And then after that, any other time that you run this code, this will just keep on existing. And you'll be able to reuse it, and it'll still be there. A lot of times, people in GameMaker, and for that matter, other languages, use static variables as a way to carry over persistent data. Like, the easiest example would be, like, you could do something like this, and it would increment every time the function was called, and you could use that to keep track of the number of times the function was called. But in my case, I'm going to use this to avoid having to allocate and clean up a lot of additional structs. Before I run this now, let me, of course, run this as it was initially. So if I say triangle versus sphere, was that a sphere? That's a sphere, like this. And if I were to profile this, we can see that the... Oh, GameMaker, why can't you give your methods more useful names to make them easier to find in the profiler? So when I do this, 100 times triangle versus sphere, we are allocating 400 new objects every time we do that. That's going to be 1 point and 3 lines. And all told, that's going to account for about a quarter of a millisecond, which isn't a huge percentage of the total amount of time that it takes to do this. I want to say that's going to be about 3%. But if we don't have to do that, and if we were to instead make a static call point, and we were to actually we can simplify that instead of copying the values over. If we were to just set the point's relevant properties, so the point's position is going to be, in this case, the nearest vector 3 to the plane, and instead of saying checkpoint new call point, we could just say checkpoint that test point. And likewise with the lines, if we were to make these static, we could say line AB dot start is going to be self.a, like this. And I'm also going to have to just dummy these out, new vector 3 when they're first defined, because the way that statics work in GameMaker is that this code will actually run before anything else in here. So if you try to say like static test point equals new call point with a vector that's been calculated somewhere else, then the game will just crash, because at the time of this being initialized, it nearest to plane won't have been created yet. But if we were to do this instead of creating a point and 3 new lines all the time, let me what was it? Triangle and sphere. And I think it does the most work when those two shapes are not in contact with each other. We've gone down a little bit, not a whole lot, but it does indeed look like we have cut out about 0.2 milliseconds out of our total frame time budget when we do this. And as with some of the other things I've touched on, this isn't going to magically make your system perform better, but it is also a bigger difference than statistical noise. And if you do enough optimizations like this, you can get a decent speed boost out of it. And just because I'm really curious, I think this is going to be the last thing I do here, but what is the collision check that like creates the most temporary structures? I want to say it's going to be triangle, triangle. It might be capsule raycast. I think I do a lot of things like that in capsule raycast. Okay, no, that's actually just mostly arithmetic. And there's a lot of vector arithmetic that you can optimize here, as we discussed earlier. But let's see, triangle, triangle has 6 points, 2 temporary triangles. Oh, you know what? This is only going to run if the 2 triangles are coplanar, and I'd have to like redesign this this testing environment to make that actually happen. So I think I'll leave that for now. Anyway, similar to the warning that I gave about removing the vector arithmetic abstractions, when and if you do things like this, do be careful to make sure that you're correctly setting the properties of the recycled shapes. make sure that you're not like forgetting to update the position of like this test point or the position of a constructed sphere or anything like that. Otherwise, you will definitely get the wrong result, and I don't think anybody wants that. You can also take this a step further. You can do this not only with call point or other collision shapes. You can do this with vectors. You can create temporary vectors and recycle those over and over again. But I don't think I'm going to show that off. I think at this point I'm kind of beating a dead horse with regards to that, and I don't want this video to be too long. So I'm going to end this off here. My name is Michael. I like wizards and dragons and making games. This is the last thing that I am going to do to this 3D collisions system in GameMaker. I will be making one more video on this that's just going to be kind of like a grand finale summary of how the project went. If you want the code for this, look for the GitHub repository down in the video description. I'm probably at some point going to update the GitHub repository to not include only the optimizations I've written out here, but also like I'll be getting around eventually to implementing the optimizations that I did talk about in all the other parts of the project. And also, if there's any other like category of optimizations that you can think of doing to the system that I haven't thought of, definitely let me know. This video has encompassed all of the things of note that I've been able to find. If you've got any good ones, feel free to tell people about it in the comments. Anyway, I try to post about 2 game dev videos a week, and I'm going to try and actually get back on that goal now that this series is pretty much done and not taking up a huge chunk of my time. I like to talk about the weirder things you can do in GameMaker, such as weird 3D shenanigans, so if any of that appeals to you, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. As you can probably imagine, this took a ridiculous amount of work to put together, so if you wanted to contribute anything, I would definitely appreciate it. Otherwise, I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Manta Ray, Syndra Larson, Squarecrow, Vitro V, and Zenjiment for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.